power transmission, construction, skin effect, and power surges.
Why use overhead lines? Quite simply, the use of overhead lines is the cheapest way of carrying electricity between 2 points over any reasonable distance. They can be installed quicker and far cheaper than an equivalent underground cable. Alterations can be carried out without great disruption to the general public or to the electricity supply, and with rigorous inspection and tree cutting regimes can give many years of reliable fault-free service. Types of poles. Firstly, let us look at the wood poles used in overhead line construction. These will be used to carry conductors carrying voltages ranging from 230 to 400 volts in LV networks up to and including 11,000 volts, 33,000 volts, and in some areas 132,000 volts. They are produced from the trunks of evergreen trees grown within the UK or imported from abroad. They are treated with a preserving agent such as creosote. A treated red fir pole can be expected to give 25 to 30 years service, but British fir or larch can last significantly less depending on location. The height and diameter of the poles will vary accordingly to factors such as required ground clearance and conductor voltage and cross-sectional area. The poles are sited in holes of depths that vary depending on pole height. Poles of up to 10 metres in height are set into holes of at least 5 foot deep, whilst poles over 10 metres high must be set into holes that are at least 6 foot deep. Once a pole being installed is level and fully aligned, a block of wood, generally a section of railway sleeper, is attached to the pole below ground, which helps to stabilise the pole in high winds. The hole is completely backfilled, usually with a concrete-like material such as permasoil added for extra stability. Once set into position, the pole is dressed with hardware and fittings prior to the installation of conductors. As we will see, the hardware and fittings will vary on the pole type and its purpose, but all poles will have the following fitted: a galvanised steel cross-arm mounted towards the top, to which will be fitted insulators to carry conductors, a yellow danger notice, a form of anti-climb device, usually featuring barbed wire to put off potential vandals. Overhead line poles can usually be described as one of the following three types: section poles, through poles, or terminal poles. Section poles are normally found wherever the line has to change direction. Two sets of dish insulators, known as strain insulators, are mounted either side of the crossarm, and to these the line conductors will be terminated and tensioned. Conductor continuity across a section pole is maintained by installing short lengths of conductor which are connected to the line conductors adjacent to the service terminations. These are usually known as jumpers. Jumpers can be defined as being either over or underslung, depending on whether they pass over or under the crossarm. In some areas of the UK, underslung jumpers may be known as loops, while overslung jumpers are also known as bows. Through poles are those poles that are used to support the conductors on straight sections. They feature pin insulators mounted on the top of the crossarm. These insulators maintain the safe clearance of the conductor from the metal crossarm. The conductor lays in a slot on the top of the insulator and is secured with a wire tie which is wound around the insulator and the conductor. Terminal poles are used near the ends of the line. Normally, the underground cable supplying the line will break ground at the base of the pole and run up it, secured by cleats, to an external cable termination. Jumpers then connect the termination to the line conductors. The crossarm used on the terminal pole is similar to that used on a section pole, but with only one set of strain insulators per phase. These crossarms are also utilised where there is a requirement to spur a section of line off the main line. The terminal crossarm supporting the end of the spur conductors would be mounted below the crossarm supporting the main line, and the two sets of conductors linked by jumpers. Two sets of terminal crossarms are often used instead of a section pole crossarm if the angle of the turn required is too great for a section crossarm. Stay wires. Wood poles supporting overhead lines can become unstable if subjected to excessive force from one direction, particularly on terminal poles or section poles on the apex of a large turn in the route. To counter this possible instability, a stay wire may be attached and tensioned to pull the pole back in the other direction. Stays are braces or cables fastened to the pole and anchored to a fixed point, usually a stay anchor which is either buried or screwed into the ground. The stay wire will feature at least one insulator in its length to prevent danger from the lower section of the stay becoming live either through accidental contact with live conductors or through inductance. Overhead line conductors. Overhead lines basically fall into 5 material groups: copper and copper alloy, aluminium alloy, BLX covered aluminium conductors, stranded steel, and aerial bundle conductor, also known as ABC. Pole mounted transformers. Transformers in rural areas tend to feed individual or small groups of customers, so are much smaller than those that feed urban LV networks. Rural overhead line transformers are designed to be mounted to the pole at high level to prevent danger to the general public from exposed HV and LV conductors. They generally vary in rating from 5 kVA to 100 kVA, and both 3-phase and single-phase units are commonly used. Larger transformers are usually installed between 2 poles with a crossarm bracer between them. This type of pole arrangement is known as an H-pole and can also be found supporting 11 kV heavy construction lines and 33 kV lines. The transformer would be mounted below the overhead line conductors and would be connected using jumpers. The LV cabling is usually wired from the transformer in double insulated conductors to LV fuse carriers mounted on the pole at a safe distance from the exposed HV conductors. From here, customers will be connected via either an LV overhead line or by LV underground cables. Overhead line switchgear. Overhead line circuits require means of isolation and protection. Rather than use ground-mounted units, switchgear has been developed to be mounted at high level on poles to provide these functions. Air brake switch disconnectors, or ABSDs, are a relatively cheap method of isolating sections of line or items of plant such as circuit breakers or transformers. They are manually dependent switches. They are operated by either handles mounted at waist height on the pole below, or a rod operated, where the operating lever is mounted at high level and is operated by insulated rods carried by the switcher. The speed of opening and closing is dependent on the switcher. Therefore, quite often, ABSDs may only be rated for dead or reduced load operation only. The ABSD takes the form of a set of blade moving contacts mounted on insulators. The incoming and outgoing sides of the ABD are connected to the line by jumpers. Overhead line protection is provided in several ways. Overhead line fuses are usually of the dropout expulsion type. When an overcurrent flows through the fuse element causing it to operate, the fuse drops out of its fixed contacts but remains hanging. This allows easy fault location identification. The fuses are installed with the same insulated operating rods used to operate ABSDs. Overhead line fuses are usually used to protect large transformers and overhead line radial spurs. They are mounted to the pole under the overhead line and are connected by underslung jumpers. Pole-mounted circuit breakers, or PMCBs. There are 3 basic types of PMCB: GVRs, PMRs, and OYTs. All are used to protect large sections of overhead line. They are all programmable to some extent, either through adjustable mechanical mechanisms on older types to electronic telecontrol panels on modern units. They usually will reclose after a trip caused by a fault on the line a number of times in an attempt to clear or sectionalize off a fault. They are all also able to be hand operated using insulated operating rods. All PMCBs are rated to at least 400 amp. Gas vacuum reclosers, GVRs. They are mounted under the overhead line they control. The GVR is a vacuum insulated circuit breaker housed within a tank filled with SF6 gas. They can be controlled locally via an electronic control panel or remotely via telecontrol. GVRs can be set up to carry out several protection functions and have many adjustable settings. Pole-mounted reclosers, or PMRs, are also mounted on wood poles under the lines they control. They are the older version of the more modern GVR and have many of the features and functions of the GVR. They are again controlled either by local control panel or by telecontrol. They tend to be much larger than the new model GVRs, and are gradually being replaced over the next 15 to 20 years. OYTs are an older PMCB design and are oil filled. They feature a mechanical recloser mechanism only and with no option for telecontrol. To this end, while the OYT is a more basic design than the GVR and PMR, with little adjustability, they are significantly cheaper to purchase, install and maintain, and so are still in widespread use, and new units are still regularly installed.
Skin effect is the tendency where the alternating current within a conductor flows around the outer edges or surface of a conductor. It works in the opposite way to a river, where the highest volume of water goes down the middle and at a higher speed. This effect is most commonly found in high voltage transmission lines. Skin effect increases resistance, the current flown, losses and heat losses. At higher frequencies, the levels of skin effect are higher. To summarise, skin effect is affected by 4 factors. Number 1, the shape of the conductor. Number 2, the type of material used in the conductor. Number 3, the diameter of the conductor. And 4, the operational frequency.
Power surges cause an abnormal supply of electrical current. The resulting waveforms after a power surge can be seen below. Power surges can be caused in a number of ways: a tree limb touching a power line, lightning striking a piece of utility equipment, or a small animal getting into a transformer. The effects of large power surges can be more detrimental. Large power surges are caused by a direct or nearby lightning strike. These surges lead to instantaneous high currents and voltages. The excessive heat caused can lead to frying parts of the circuit. These types of power surge are rare in the UK due to the irregularity of a lightning strike occurring. The effects of low-level power surges won't cause the immediate damage that a large power surge would. However, gradual deterioration of internal electronic circuitry will occur. The long-term effects of this deterioration is for the device in question to fail. Small surges can occur hundreds of times a day. These are harmless and cause no damage to the network or any of its components, and typically go unnoticed.
One type of surge protection are surge arresters. Surge arresters are used to protect high voltage equipment in substations such as transformers, circuit breakers and brush-ins against the effects of overvoltage caused by incoming surges. Some overvoltages are very high in energy. The current from the surge is directed through the arrestor and in most cases to earth. Effective overvoltage protection requires different surge arrestor types to be used according to the particular application. There are 3 main types: surge arresters with porcelain housing, surge arresters with silicon housing, and surge arresters with metal enclosures. During normal operation, a surge arrestor should have no negative effect on the power system. Moreover, the arrestor must be able to withstand typical surges without incurring any damage. Non-linear resistors made of metal oxide fulfill these requirements thanks to the following properties: low resistance during surges, so the overvoltages are limited; high resistance during normal operation to avoid negative effects on the power system; sufficient energy absorption capabilities for stable operation. Another type of surge control is the overhead earth wire method. The overhead earth wire with suitable cross-section is placed above the transmission conductors at the top of the transmission towers. The earth wires are then grounded at each tower. When lightning strikes, the electrical potential is diverted through the earth wires to the towers and then down to earth, protecting and preventing a direct strike on the transmission conductors. Thank you for listening.